Hello, my name is Udo Welzel. I'm working for Robert Bosch Automotive Electronics in Germany, and together with my colleague Norbert Holle, I have prepared for you a lecture dedicated to the update of the automotive addendum to J Standard 001 and IPC A610 to revision level H. Before we go into those technical details, I would like to start with a general introduction why such an automotive addendum is important. If we look to global megatrends in our society, we can basically notice four such megatrends. There is connectivity. By 2020, 50 billion things will be connected. There's urbanization. 60% of the world's population lives in cities. There are significant changes in demographics. The cohort of people aged 65 or over is growing twice as fast as all the others. And last but not least, there are significant challenges related to energy and climate, namely that the probability that global warming will be limited to just 2 degrees centigrade is very low. Now, if we talk about those global megatrends for our society, they of course also have an impact on the automotive industry and on automotive electronics in particular. And in this context, many different topics could come to your mind, and I've tried to list some of those which could come to your mind at the bottom of the slide. But if we think about those topics in detail, we can basically narrow down these topics into three megatrends which are relevant for the automotive market and automotive electronics in particular. And those three megatrends which are relevant are automated mobility, electrified mobility, and connected mobility. Here I've listed these threse important megatrends for automotive electronics again on this slide. And when we think about these megatrends, we should always keep in mind what are the criteria that make automotive electronics special. In this lecture, I will frequently use the abbreviation ECU for electronic control unit. So in automotive electronics, these are mission-critical ECUs. In the IPC scheme, this means they belong to class 3 products. These ECUs are supposed to be used in harsh environments. This is another important identifier for a class 3 product. But of course, there are many other industries where also the ECUs are mission critical and are used in harsh environments, for example, in the aerospace industry. So what makes automotive electronics special? What makes automotive electronics special is that they are really produced in very high volumes. So these are the three characteristics which make automotive electronics special and which also make those different from other industries which pertain to IPC class 3. Now, thinking about the future, because we have been talking about megatrends, there are again many different topics which may come to your mind. I've listed some of them here. For example, connected mobility brings about the use of 5G, of commodity components, changes in transmission and protocols. The automated mobility brings about, as an example, an increase in the power density in logic ECUs, involves high-speed design, further miniaturization, and electrification is related to the use of even higher voltages, the 24/7 operation of ECUs as an example in the context of the charging infrastructure. And this means that the three megatrends, connected mobility, automated mobility, and electrification, they drive continuous evolvement also of the technology in automotive electronics. This all combined justifies that we, on the one hand side, have dedicated standards for automotive electronics, and that we also continuously have to evolve these standards, update these standards to assure that they are always up to date with the ever-changing technology used in automotive electronics. So one such document is the automotive addendum to J standard 001 IPC 610. It's not the only document dedicated to automotive electronics, but this is the document I would like to focus my attention on for the lecture today. You see here the title page of the automotive addendum to J standard 001 and IPC 610 revision level G. And this automotive addendum provides requirements to be used in addition to, and in some cases in place of, those published in the base documents. So the base documents are J standard 001 and IPC 610 for the automotive addendum, which you also can see here on the screen. So that means that the automotive addendum shall be used in conjunction with the base documents, and the base documents to be used shall be of the same revision level as the automotive addendum adopted. Here's a little sketch how this is organized at IPC. So the task group in charge of the automotive addendum is the 7-31 BV task group. And if the subject matter experts in the 7-31 BV task group develop technical content, and if this content is specific for automotive electronics, then it should enter into revisions of the automotive addendum. But sometimes it can also happen that the technical content developed is not really specific to automotive electronics, but could also pertain to other industries. In these cases, the technical content should be brought forward to the respective task groups of the base documents. So that means to the 7-31B task group in case of technical content that belongs to IPC 610, or to the 5-22A task group in case of technical content that belongs to J standard 001. So the automotive specific content should be related to this unique combination of mission critical plus harsh environment plus high volume automotive production. This is basically what we should cover in the automotive addendum. If we have technical content that is not automotive specific, this should be brought forward to the respective base documents. Here on this slide, I have basically outlined for you the history of the automotive addendum to J standard 001 IPC 610. The task group co-chairs are listed here. So there's Gaston Hidalgo from Toyota Motor North America, Jose Servin from Vitesco Technologies in Mexico, and myself from Bosch Automotive Electronics. And we also have a vice chair, that is Tino Gonzalez from ACME Training and Consulting. You see that we started our work way back in February 2017, and on this time axis I have essentially listed face-to-face meetings, with the exception of APEX 2021, which was, due to the impact of the pandemic, a purely virtual event. And of course, those face-to-face meetings were complemented with numerous online meetings. You can also notice that due to the impact of the pandemic since APEX 2020, we had fewer face-to-face meetings. So online meetings became more important in this time frame. The first edition of the document was made available in February 2020 after roughly 3 years of work on the document. And as soon as this document was published, we immediately started working on the next revision level H. And this document was technically ready already in October last year, but of course there is still some work related to typesetting and making it ready for publication, proofreading, and so on. And it should be made available soon. Apex in this year was again a face-to-face event, but of course participation from Asia was lacking due to the lasting impact of the pandemic. There was mostly participation from Europe and North America. And moving on into the future, of course, we have to make sure that inputs from Asia are appropriately considered. So we will make sure that there are enough virtual meetings to enable good collaboration and interactions also with colleagues in Asia. And of course, we all hope that the impact of the pandemic will diminish and that in the near future we will again have the possibility to get back to global, worldwide face-to-face meetings. So as I've already pointed out, the Automotive Addendum Revision Level H will become available roughly in February 2022. So at the time that you listen to this lecture, the document may already be available for you. And of course, we have already started to work on RefJ. Talking about the technical content of the document, I would like to first start with a general remark. There are, of course, some component styles which are not covered in the base documents because they are not widely enough industrialized in other industries, but are already used in automotive electronics. So these components are covered in the automotive addendum, and I'm giving here you 3 examples. So coil terminals consisting of coated wire, they are covered in section 8.3.22 of the automotive addendum. These L-type fuses and shunt resistor terminals are covered in section 8.3.23. And last but not least, these half-moon shape ferrite termination coil terminals are covered in section 8.3.21. So the automotive addendum provides a possibility to cover component styles which are widely industrialized in automotive electronics, but which are not that widely used in other industries, to enable covering these component styles already in the base documents. Of course, over time, they may move over to the base documents, but for the time being, they are covered in the automotive addendum only. Now, talking about major changes related to the release of revision H, which is the main topic of this lecture, I'm giving here some examples. In alignment with the base documents, the target conditions have been dropped from the document. That was a very controversial discussion, but at the end it was concluded, or agreement was reached, that to align with the base document, target conditions should be dropped. And then if we talk about other major changes and additions, so new content as an example was added for threaded fasteners and other threaded hardware to section 4.1.5.4 in the A610 part of press fit. In sections 4.3.2, 4.3.3 and 4.3.4 was harmonized with IPC 9797. You may know that IPC 9797 is a standard dedicated to compliant press fit technology in automotive electronics and other high reliability electronics. And of course, it was logical to harmonize the content of the automotive addendum with IPC 9797. Section 10.8.3 of A610, the coating thicknesses in table 10-1 HA were adjusted. And last but not least, and this is the focus for the remaining part of today's lecture, new content was added for voiding and solder coverage in a totally new section 7.0.1, the 001 part of the automotive addendum JA. So I would like to talk about this in some more detail. If we think about voiding, for a long time there were lots of controversial discussions in different industries, but particularly also in automotive electronics, where on the one hand side, some customer specifications from automotive OEMs imposed requirements on voiding, which were quite challenging. On the other hand, throughout the supply chain, there were lots of discussions what appropriate requirements could be. And to reach consensus in the automotive electronic supply chain, we basically think that 3 important steps have to be taken to reach such consensus. First of all, consensus has to be reached regarding typical components, printed boards, assembly materials and processes. Then consensus has to be reached regarding typical performance, functional characteristics and the impact of voids on function. Consensus has to be reached regarding typical environmental loads and impact of voids on solder joint reliability. Once such consensus among stakeholders in the supply chain is achieved, then voiding criteria or requirements can be established and documented in industry-specific addenda, for example in the automotive addenda. We've been discussing this topic in the 7-31 BV task group for quite a while, but without being able to establish some consensus. And for that reason, I have taken another approach, and I have tried first to establish consensus in a smaller group. And this was a German working group for assembly and interconnect technology of automotive electronics, which had been established in 2017. These are activities within the DKE, the German Electrotechnical Commission, as working group 682.0.7, assembly and interconnect technology in automotive electronic assemblies. This working group has a broad coverage of the automotive supply chain. Vice chairs come from Volkswagen and Continental. I myself am the chair of this group. And we also have a good coverage of OEMs. So Audi, BMW, Volkswagen belong to this working group. We have a good coverage of Tier 1 and EMS. I will not read out all the details. You can read for yourself. Also of the Tier N. And even we have participation from other stakeholders like academia, testing and training laboratories, and for example, aerospace. And after continuous work within this working group, we have been able to establish consensus among the stakeholders in this supply chain. Document was developed in the International Electrotechnical Commission, IEC Technical Report 61191-8, and this contained basically the consensus established within this technical content was taken over, and the requirements developed were proposed to the 7-31 BV. On this slide, you can basically a summary of the developed requirements for different component styles. Requirements were developed in terms of voiding or solder coverage. I will talk about that in a little bit more detail shortly. And as this is a very, very busy table, we will not go through it line by line, but we would focus on some major topics from the table. Not all kinds of voids can be detected in 2D X-ray imaging under mass production conditions, and therefore some of these voids need to be excluded from the criteria. I will show you shortly how we have implemented this. And secondly, we will take one example, for example, in the transistor, the thermal plane termination, and I will explain you how the requirements have been implemented now in the automotive addendum. To give guidance on different types of voids, the appendix AH has been added to the automotive addendum. So this is a summary of different types of voids which can occur, whereby the criteria developed for voiding and solder coverage only pertain to the macro voids and the design-induced voids. The other types of voids can typically not be detected in 2D X-ray imaging in mass production, and care has to be taken to avoid these types of voids already in the development phase, where with cross sections one has to make sure that these types of voids are not relevant. So the appendix AH added to the automotive addendum provides guidance on the void categories. Then we have introduced a very important notion of solder coverage. The solder coverage is obtained by dividing the overlapping area between parallel and wettable surfaces of printed board and component termination covered with a vertically continuous layer of solder by the total overlapping area between parallel and wettable surfaces of printed board and component termination. Voids and empty space are not part of the vertically continuous layer of solder and therefore do not contribute to the solder coverage. Now, this sounds pretty complicated, but I will try to explain you in a very simple manner what this type of calculation is about. So this solder coverage is basically used for all component styles containing requirements in the automotive addendum, except for. Now with this slide, I would like to explain a little bit in more detail what the solder coverage is about. So basically we see here components soldered to a printed board. This here is the thermal pad of the component. And in this case, you see a solder joint which basically is covering both the area on the component, the thermal pad area on the component, and the corresponding soldering area on the PCB. So if you would look in an X-ray image, you would see a continuous layer of solder. That means the coverage is 100% because the overlapping wettable area on PCB and component is by 100% covered with a continuous layer of solder without voids, so the voiding is 0% here. This is of course not a very realistic example. Now let's look at another example. So here in this case you have a couple of voids. So the voiding level in this case is 30%. And to calculate the coverage, you have to determine the area in this X-ray image which is covered by solder with respect to the wettable overlapping area both at component and PCB side. And in this case, the solder coverage amounts to 70%. Now here you see another example where, due to a lack of solder, the overlapping wettable area between component and PCB is not completely filled with solder. This could, for example, be the case if not enough solder has been printed to entirely fill the available wettable area on component and PCB side. And in this particular example, I have drawn an example where there are no voids. So the voiding in this case would be 0, but the coverage would still be only 70%. This explains why the solder coverage is in general a much more useful characteristic for most types of solder joints. So it is used except for ball grid array components. So this is now an example how the requirements have been implemented in the automotive addendum. Look here at the example of our transistor. The acceptable condition is that the solder coverage is equal to or exceeds 35%. The defect condition is if the solder coverage is less than 35%. In addition, we have introduced the process indicator condition because we have noticed that the solder coverage can show quite large statistical scatter. This average solder coverage is calculated from at least 25 solder joints of a particular component part number and case size from at least 5 different non-consecutive panels. It is a process indicator condition if this average solder coverage lies between 35% and 50%. So that means it's a process indicator condition if you have an average solder coverage less than 50%. We have also added additional illustrations. This is an example for ball grid arrays, where these additional illustrations show defect and acceptable conditions for ball grid array solder joints. Okay, I would like to come to the end of my presentation and provide you with a summary. So keep in mind, in general, the automotive addendum to J standard 001 and IPC 610 provides requirements and criteria to be used in addition to and in some cases in place of those in the base documents. A major revision for the revision level H is related to the coverage of voiding and solder coverage. As voiding is typically not critical for solder joint reliability and function under standard, well-controlled production conditions, it was possible to establish consensus on voiding and solder coverage requirements, even though individual voiding requirements of automotive customers were often not compatible with typical process kata for voiding. So this consensus in the supply chain of the automotive electronics had to be established and documented in automotive addenda. Consensus on requirements and acceptability obtained at the DKA working group AK 682.0.7, which provides a broad coverage of the supply chain, resulted in the publication of International Electrotechnical Commission Technical Report 61191-8, which served as a basis of discussion also within our IPC Task Group 7-31BV. By taking over these requirements, the addition of voiding and solder coverage for revision H of the automotive addendum is an important step towards the harmonization of these requirements throughout the supply chain. With this, I would like to close the lecture. Hope that you stay healthy. In the near future, we can again have an in-person event and a face-to-face discussion. But if you have any questions or comments, please get back to me by email. Looking forward to your comments, and I will be happy to discuss those with you. Thank you very much, and goodbye.